Section: Introduction. In this section, we outline our method aimed at guiding large language models, LLMs, to generate responses in two parts. 1. A reformulated version of the original question with XML tags highlighting key facts, and 2. An answer that connects statements in the response to the tagged facts. We believe that generating these tags will help LLMs focus more on the important facts, which should reduce inaccuracies and improve the final answer. Additionally, we think that presenting these highlights to humans will enhance their ability to verify the information. We experimented with various XML tag formats and found that using tags like less than fact1 greater than, less than fact2 greater than, etc., yields the best accuracy from the LLMs. To encourage LLMs to produce highlighted chains of thought, HoTs, we developed a specific prompt structure that we applied across all datasets. This structure includes 8 demonstration examples that show LLMs how to insert tags while answering questions. We also provide a clear instruction for LLMs to tag questions and their answers. Since each dataset may require different linguistic structures, we created separate examples for each dataset to guide the LLMs effectively. To gather human-annotated HoT demonstrations, we recognize that it can be time-consuming for people to create these, especially across 17 datasets. Therefore, we propose a 3-step, LLM-assisted method to help humans quickly generate high-quality HoT demonstrations. First, we manually annotate 15 question-answer pairs with highlights from various domains. Next, we use these annotated examples to prompt LLMs to create additional demonstrations for each dataset. In the first step, we select 15 HoT question-answer pairs from different datasets and manually add XML tags to highlight key phrases. We follow a principle where a fact is a crucial phrase that, if removed, would make the question unanswerable. We ensure that any irrelevant details are not tagged. After tagging the questions, we identify corresponding phrases in the answers and tag them as well, ensuring that every tag in the answer matches a tag in the question. These 15 annotated examples serve as meta-demonstrations for the LLMs. In the second step, we need to create 8 HoT demonstrations for each dataset to compare HoT and CoT fairly. We ask the LLM to generate standard CoT answers for 8 random questions and then convert these into HoT examples using our meta-demonstrations. In the third step, we prompt the LLM to take the 15 demonstrations and a question from the previous step to produce a reformatted question with XML tags, resulting in 8 tagged questions. We then instruct the LLM to use these tagged questions along with the 15 demonstrations to generate tagged answers, giving us 8 pairs of tagged questions and answers for each dataset. We evaluate our method across 17 tasks in 4 domains: arithmetic, question answering, logical reasoning, and reading comprehension. For arithmetic, we test on tasks from various datasets, including GSM-8K and multi-arith, and also assess performance on RGSM and GSM symbolic. For logical reasoning, we select 5 tasks from Big Bench Hard. In question answering, we use Strategy QA, SPART QA, and Date Understanding. Lastly, for reading comprehension, we utilize subsets from the drop benchmark. Section Summary. In this section, we describe our method for prompting large language models, LLMs, to generate responses that include XML tagged key facts and corresponding answers, aiming to enhance accuracy and reduce hallucination. We outline a 3-step, LLM-assisted approach for creating highlighted chain of thought demonstrations across 17 datasets, which involves human annotation followed by LLM generation of tagged responses. Section: HoT consistently improves LLM accuracy across models and datasets compared to CoT. In this section, we demonstrate that HoT consistently enhances the accuracy of large language models, LLMs, across various models and datasets when compared to CoT. We believe that HoT prompting helps LLMs to recognize and utilize relevant facts in the questions, which may lead to more accurate answers and fewer errors. To test this, we compare 8 examples of CoT and HoT using 5 different LLMs, including both proprietary and open-source models, across 17 tasks. The main distinction is that HoT examples include XML tags, while CoT examples do not. Our results show that HoT generally outperforms CoT in most cases. On average, HoT improves accuracy in arithmetic, question answering, and logical reasoning tasks by 1.6, 2.58, and 2.53 percentage points, respectively. While some datasets see larger improvements, others like GSM-8K show only modest gains, possibly because CoT scores are already very high. However, in more challenging versions of GSM-8K, HoT shows significant improvements. We also conducted an ablation study to identify which components of HoT contribute to its success. HoT involves two steps: regenerating the question with XML tags around key facts and tagging the answer. We found that simply repeating the question can enhance accuracy. Our study compared several variations, including repeating the question alone, adding tags to the question, tagging the answer, and the full HoT approach. Our findings indicate that all variations outperform the baseline CoT. For smaller models, adding each component consistently boosts accuracy, while the effect is less pronounced for larger models. Notably, adding tags only to the question or answer yields smaller gains compared to the full HoT method. Interestingly, even when instructed to tag only the answer, larger models still generate tags in the questions, leading to improved accuracy. Overall, our results suggest that the best performance comes from using tags in both the question and answer. Section Summary. In this section, we demonstrate that HoT prompting significantly enhances LLM accuracy compared to CoT across various models and tasks, particularly in arithmetic, question answering, and logical reasoning. Our ablation study reveals that the combination of tagging both questions and answers yields the best performance, while each component of HoT contributes positively to accuracy improvements. Section: Tagging arbitrary phrases in the answer hurts HoT accuracy. In this section, we explore how tagging random phrases in answers affects the accuracy of our HoT, highlight of thought, approach. Since the key facts are already tagged in the questions, we question whether the tags in the answers need to match for HoT to function effectively. To investigate this, we maintain the original HoT examples but randomly relocate the tags in the answers. We then assess how this mismatch influences the accuracy of 4 models across 7 datasets. Our experiments reveal that mismatched tagging leads to an average accuracy drop of about 2.13 percentage points. However, this impact varies significantly by dataset. For instance, the accuracy decrease is much greater in Aqua compared to GSM-8K. This suggests that when LLMs encounter mismatched tags in Aqua, they are less likely to generate tags in their responses, leading to poorer performance. Despite the mismatched tags, HoT still outperforms CoT by 1.21 percentage points, indicating that LLMs can still learn from the few shot examples and apply correct tagging to new questions. We also examine how our HoT highlights in LLM answers affect user decision-making accuracy and time. Users are tasked with verifying whether the final answers to arithmetic questions are correct based on the input question, the HoT chain of thoughts, and the LLM's predicted answer. We believe this is the first study to analyze the impact of highlights in chains of thought on user performance in a downstream task. To evaluate this, we measure user accuracy in verifying LLM responses for arithmetic and reading comprehension problems. We create a balanced set of correct and incorrect responses for users to assess. We recruit 63 users, each verifying 10 LLM responses, and they are randomly assigned to review either HoT or CoT responses without any external aids. Our results show that users take nearly 25% less time when making decisions with highlights, which aligns with previous findings. However, user accuracy varies. They perform better on correct cases but worse on incorrect ones, suggesting that HoT highlights may lead users to mistakenly believe an answer is correct. This unexpected finding highlights the need for further research on how to effectively use highlights in LLM chains of thought, especially as they become more prevalent in search engine results. Section Summary. In this section, we investigate how mismatched tagging in answers affects the accuracy of the HoT method compared to CoT, finding that while mismatched tags reduce accuracy by an average of 2.13 percentage points, HoT still outperforms CoT. Additionally, we assess the impact of HoT highlights on user verification tasks, revealing that highlights can speed up decision-making but may also lead users to overestimate the accuracy of LLM responses. Section: HoT is estimated to improve user verification accuracy on all 17 datasets. In this section, we estimate that HoT improves user verification accuracy across all 17 datasets. Since testing all users on these datasets is impractical, we compare verification accuracy when highlights are used versus when they are not, specifically looking at HoT against CoT. We determine the verification accuracy of users on a dataset based on the actual accuracy of the language model for that dataset, along with human accuracy scores for correct and incorrect cases. We observe that language models generally achieve around 80% accuracy on most datasets, and we find that the average estimated verification accuracy of HoT is about 3.33 points higher than CoT across 5 language models. Importantly, HoT does not negatively impact the accuracy of language models as verifiers. Instead of having humans verify language model answers, it is becoming more common to use other language models for this task, which can reduce human effort and promote self-improvement. We also examine whether providing HoT answers to language models affects their ability to verify the accuracy of those answers. Our tests on various models, including GPT-4o and GEMINI 1.5 Pro, show no consistent pattern indicating that highlights either help or hinder accuracy across different models and formats. We hypothesize that while language models can track facts in answers using HoT, incorrect answers may stem from information not included in the tags. We acknowledge some limitations in our approach. The process of regenerating questions with tags can lead to models misformulating the original question or not following the tag format correctly. Larger models tend to perform better in adhering to the format, while smaller models may struggle with consistency. These challenges highlight the need for improved tagging behavior across different model sizes. Additionally, while reasoning models like DeepSeek R1 can generate highlighted responses effectively, we do not see an improvement in benchmark accuracy with HoT compared to CoT. This aligns with warnings from DeepSeek R1 authors that few shot examples can sometimes hinder model performance. Our findings suggest that HoT highlights may lead users to overtrust language model answers, even when they are incorrect. Looking ahead, we propose that HoT may enhance LLM accuracy by encouraging the generation of matching tags in both questions and answers, which could increase attention to those tags. Future research is necessary to confirm this idea. We also see potential in having language models highlight derived results and reference them in later parts of the reasoning process. By tagging both explicit facts and intermediate results, language models can assist users in verifying and understanding complex reasoning more clearly. Currently, we use few-shot demonstrations to guide language models in generating tagged questions and answers, but we believe that fine-tuning models to produce HoT directly could be a valuable direction for future work.